Okay, so we've been talking about KSP here. Remember, KSP is really was referred to as the solubility product. It is essentially the equilibrium for things that are typically insoluble. Um, so they always have sort of the same setup in terms of when you write a reaction, sort of what goes on the reactant side, what goes on the product side, and that is here. We always have the solid on the reactant side. We always have our aqueous sort of ions here on our product side. So what that means is when we do deal with sort of KSP type problems, we pretty much write the expression basically based off of just the products, really. Again, because our reactants are solid, so they're not included like a normal equilibrium type of expression. Also, we see that these guys are very small values, and that also makes sense since they are for things that are typically insoluble. So they're for things that we typically obviously associate as solids, which means that the equilibrium would lie, you know, towards the left here. And that does make sense as to why we do see very small values for KSP. You know, something like, again, silver chloride, something that we typically think about as being insoluble in a solid, even though, as we talked about last time, even though something is technically sort of listed as a solid and insoluble based on, say, something like solubility rules, there is some degree of solubility with everything. So even something like silver chloride, which, you know, 9 times out of 10, if you want to think about it that way, is pretty much going to be a solid. A little bit of it will break apart. So there is just a little bit of those ions still floating around in the solution. It's able to set up this equilibrium. Again, a very small amount in most cases, because, again, the equilibrium is lying more towards the left-hand side. So we talked a little bit about the idea of solubility and things that sort of affect solubility. And one thing that affects solubility is something like the common ion. So we did some problems last time about common ions. And it basically, for example, if we were doing this and we had some sodium chloride in there, that would obviously supply some chloride. That would be like adding the chloride, which would cause the equilibrium to shift to the left. And what that would mean is we would have more solid at that point and basically keep the solid together. It basically will kind of decrease the solubility of something like silver chloride as well. Again, just like it does with a weak acid or weak base, it keeps those guys together. Same idea here, that will keep basically the solid together, in this case, some type of common ion. We do KSP problems a couple of ways, as we talked about. One way is if we're just given the KSP, we do an ice table. The difference in the ice table is that we oftentimes will use the letter S instead of X. And S, again, represents the molar solubility. Works basically the same way as X like we do in normal tables. Again, though, we just sort of solve for it sometimes using S. And again, that is technically, when you do solve for S, the solubility of the whole compound, like silver chloride. I think we had an example earlier. And again, stoichiometry wise, we still do the same stuff. You know, if there was a 2, obviously there wouldn't be in this case, but if there was a 2, we would do 2s here plus 2s and stuff like that. So we still take in, obviously, the coefficients when we do those things. Any questions on any of that there that we talked about last time? Okay, so the next thing we're going to talk about is actually another thing that really does affect solubility, and that's a big thing, which is pH. So pH has a pretty good effect on the solubility of certain compounds. And playing with the pH, either making it more acidic, more basic, you know, it can help in either allowing things to sort of dissolve, or in certain cases, as we'll talk about here, there may be situations where you don't want something to precipitate out. So you may want to keep it in solution. So pH can play a pretty good effect in both of those things. Now, the presence of a common ion, as we just saw and talked about last time, does decrease that solubility. When we play with sort of the pH of a solution, If we have an insoluble base, it typically will dissolve in acidic type solutions. And if we have an insoluble acid, it typically will dissolve in basic solutions. So let's take a look at one here, like magnesium hydroxide. If we were to write the KSP expression for magnesium hydroxide, again, it would be our product, so the concentration of magnesium ions times the concentration of hydroxide. Again, here we would square it because of the coefficient that we see here. So if we run through sort of our normal KSP type table like we've done previously in this chapter, we would start with zeros here. So if we did sort of our KSP, actually what I'm going to do is just going to rewrite that KSP over here so it gets it kind of out of the way a little bit. KSP is 1.2 times 10 to the minus 11. All right, so I'll just borrow this, I think. So initially here, 0 and 0. Change would be plus S and plus 2S again for the coefficient, which means when we reach equilibrium, we have S and 2S. So if we were running through like our normal, again, sort of KSP type table, we would then put those guys into our expression here. And that would give us S times 2S squared is equal to 1.2 times 10 to the minus 11. Here, doing some of the math, we end up with 4S squared becomes 4S cubed is equal to 1.2 times 10 to the minus 11. Dividing that 4 to the other side there, gets us S cubed is equal to 3 times 10 to the minus 12. Taking the cubed root there. Again, if you don't have a sort of cube root type button, you could do the kind of up to the top caret. 1 divided by 3 will do that for you. And that will get you an S that is 1.44 times 10 to the minus, what we got there, 4, looks like. Any questions on that calculation? So that calculation, again, is a basic sort of KSP type calculation. It does give us a couple of things that's kind of important, obviously, in terms of pH. So if we think about pH, right, obviously pH is minus the log of the H plus. We obviously don't have H plus here since we're dealing with a base, but we can look at POH, right, which is minus the log of the OH minus. So in this particular sort of insoluble base here, it is the hydroxide here that would allow us to get sort of a baseline pH. So in this case, the hydroxide concentration at equilibrium, as we can see, is equal to 2S. So if we take 2 times 1.44 times 10 to the minus 4 molar, that will give us a hydroxide concentration of 2.88 times 10, and that also looks like a minus 4. That will allow us to calculate, again, not the pH, but the POH, and the POH here would be minus the log of that. Gets us a POH of 3.54. And from that, now we can get the pH by taking 14 minus 3.54. That gets us 10.46 as our pH. Any questions on sort of that number there, or how we got to that number? So what is knowing sort of the pH in the solution? Why would it be important in terms of solubility? So let's talk a little bit about this. So what we basically just calculated is if you had sort of a beaker of the solution, the baseline pH of the solution right here is 10.46, which means What would happen if we took the pH below 10.46? So if I took the pH below 10.46, what would I have to do that? That means I probably would need to add some acid. And when I would add some acid, what I'm really adding, right, is H plus. So let's think about the actual reaction here. Actually, let me rewrite it here. And when I would add H plus to this sort of equilibrium here, there really is no H plus in it. But when we add H plus to a system that has OH minus, these two guys really like each other. And basically these two guys will then make water, right? That is essentially removing from this equilibrium OH minus. And what does that mean in terms of Le Chatelier's principle? If we remove that OH minus, we would expect the equilibrium to now shift towards it. So the equilibrium should shift towards it. In the process of doing that, that would mean that we would be going from more solid to more aqueous ions. We would actually be increasing the solubility. Any questions on that? And that is exactly what this sentence means, that if we have an insoluble base like magnesium hydroxide and we add acid to it, by supplying the acid, we're supplying more H plus. More H plus will remove hydroxide from that equilibrium, causing the equilibrium to shift to the right. And that essentially means that we have now increased the solubility. We're going to have more of the solid basically dissolve. Any questions on that? So obviously, let's talk about sort of the opposite approach here. What happens if we take the pH above 10.46? Again, here, in order to increase the pH, we need to add base. When we add base, what are we really adding? We are really adding hydroxide. So let's take a look again at this equation. And see what the effect that would have on it. Well, in this case, hydroxide is part of the equation or the reaction, hydroxide and both. So essentially, by adding the base to this solution, we're basically increasing this or adding more. And when we add more based on Le Chatelier's principle, that would cause the equilibrium to now shift away from it. When it does, we are now actually going in a direction of more aqueous ions heading towards more solid being formed. We're actually decreasing the solubility here. Again, by adding that base, we're increasing the hydroxide, going to force the reverse reaction to occur, basically closing down basically any of that guy from dissolving, and again, decreasing the solubility of that. Any questions on either of those things? Acids work the same way. If you have an insoluble acid, it would be more soluble in a basic type solution. And if you have a insoluble acid, it would be less soluble in a more acidic sort of solution. Now, you may be wondering, does it have to be like straight on acidic type in terms of the solution? And what I mean by that is this is why this right here, this sort of baseline pH is really important, because I don't necessarily, for example, in this case, I don't necessarily have to actually get the pH, say, below, below 7. I could actually bring it down to like 9. I could bring it down to 8. And you will see a pretty big increase in the solubility by, even though the pH is still basic, it is more acidic than sort of the baseline pH for the solution. So again, in this case, 10.46 is like our baseline. Even if we brought it down to like a pH of 8, you would see a very big increase in the solubility of that salt. Again, even though it's technically still basic, it's much more acidic than it would be in its normal sort of situation. So that's why, if you have a case like this, understanding sort of where the baseline pH of this particular solution is, just adjusting a little bit up or a little bit down can be enough in certain cases for you to see a significant either increase or decrease in sort of the solubility. So again, just to be clear, you don't have to drop it all the way down to like below 7 to actually see something occur. You just need to make it more acidic in this case than where it started from. Or if you make it more basic from where it started from, you obviously see the opposite occur. Question on that? Okay. pH is a very important thing in terms of solubility, as we just saw. Again, and it has an effect on it. There's experiments. We don't do that here, these experiments anymore at this school, but there used to be a big amount of experiments, which are known as qualitative analysis. That's very commonly done in this class. And it's basically all about that, all about sort of solubility and precipitates and making things stay in solution, taking things out of solution. And one way that we can accomplish that in these type of experiments is to really kind of play with the pH, and there's some crazy steps sometimes when people do these types of experiments that, people really don't understand sometimes. In the same like sentence or two sentences, it says, hey, make the solution acidic, then make it basic. And, by playing with these pHs, again, the goal in sort of this qualitative analysis type experiments is to keep certain ions in solution while allowing other ones basically to precipitate out. So pH is a very good way of kind of doing that. So common ion is really important in terms of whether or not sort of solubility or the effect on solubility. pH also very important. Another thing we're going to look at now is kind of the third thing that's really important in terms of sort of solubility. And that is, for example, whether or not a precipitate will form. But really what we're looking at here is concentration. It's kind of the third thing that's really important in terms of whether or not you would technically see perhaps a solid form or not a solid form. Again, as I mentioned earlier on this chapter, sometimes we think about solubility rules as sort of 100% always correct in every situation. And it's not always correct in 100% of the situations. There are some factors that really account for whether or not you may see a solid or whether or not you may not see a solid, even though solubility rules say when these two guys come together, you should see a solid. So one thing that affects, as we just talked about, common ion. Another thing is pH. And what we're going to really talk about here is really concentration is another thing that has a big effect on whether or not you'll actually see a precipitate form, even though technically based off of solubility rules, you should expect to see a precipitate form. So how do we sort of look at that? Well, when we're sort of comparing whether or not, say, for example, we take two solutions, and in those solutions, there's a cation and an anion, which is known by solubility rules that, if they come together, we're going to make this solid. When we pour these guys in. So to see whether or not this will actually occur, we again, as we talked about at the very beginning of this chapter, we could look at something like Q. Q again is the reaction quotient, and it is calculated the same way as KSP, which means in this case, we're basically taking just our products. And we could compare it if Q is greater than the KSP, then again, you could go opposite of the way it's pointing, and that would take you to the reactant side where we have more solids. occurring, and we would expect a precipitate to occur. And vice versa, if we calculate Q and it's less than the KSP, again, you could go opposite of where that's pointing. That would take you to the reactant side, where we would not expect to see a precipitate occur. So let's take a look at an example here and try to figure out, will we see a precipitate occur or not occur in this particular case? So if we take, excuse me, if we take 2 milliliters of a 0.2 molar sodium hydroxide solution and we add it to 1 liter of calcium chloride, the question is, will we get a precipitate basically to occur? So the first thing you want to think about is, are there anything that will basically make a precipitate, right? So based on solubility rules, are there anything that will come together to actually form a precipitate? That requires you to think about the two things that you're mixing. And in this case, we're taking calcium chloride, which is basically a source of calcium ions and chloride ions. And we're taking sodium hydroxide, which is a source of sodium ions and hydroxide ions. So obviously sodium hydroxide is a solution, calcium chloride is a solution. So really your two options is these guys are basically going to switch partners, right? Which is basically a double displacement type reaction. So will a combination of sodium chloride make a solid based on precipitation solubility rules? And the answer is no, these guys typically do not. Calcium hydroxide is a possible precipitate based off of sort of solubility rules. So based off of solubility rules, it is possible to form a calcium hydroxide precipitate. So the question then becomes, in this particular situation, will it form? And that's going to require us to calculate Q. So to help us sort of decide that at the end, if we look up the KSP value in a table, the KSP value for calcium hydroxide is 8 times 10 to the minus 6. So what are we wanting to look at? Well, if we look at calcium hydroxide and we set up its equilibrium, it's going to break apart into calcium ion and a couple of hydroxide ions. That obviously is the KSP that we just got right there. Now, that means in order to calculate Q in this case would be the concentration of calcium times the concentration of hydroxide. And again, we do need to square it here. So we basically need to figure out the concentration of calcium and the concentration of hydroxide that's present. So let us start with the calcium here. In this case, if we're dumping these two solutions in, the only guy that's got calcium is this guy right here, right? So we need to figure out what is the concentration of calcium. And when we have something like calcium chloride, when it breaks apart, you get a calcium plus 2 chlorides. And that is basically a 1-to-1 relationship between those two, which means we just need to figure out the concentration of this guy. Now, the concentration of this guy is not 0.1 anymore, because remember, we're basically taking like a beaker or something and we're dumping in 1 liter or 1,000 milliliters, if you will, of the sodium hydroxide. I'm sorry, of the calcium chloride, actually. And in there, we're also dumping 2 milliliters of the sodium hydroxide. So our total volume, when it's all said and done, is 1,000 milliliters for the calcium chloride plus 2 milliliters for our sodium hydroxide. That's 1,002 milliliters. Basically, here is our total volume. You can also convert it to liters if you like. And I need that because basically what I'm doing here is a dilution, right? So I need to do M1 V1 is equal to M2 V2. Here, the hydroxide concentration would be my M1, which is 0.1 molar. My V1, which is 1 liter. I'm just going to convert it into milliliters. You could leave it in liters if you want. And I did that because I did my total volume in milliliters. That way, again, the milliliters will cancel. Again, you can do both of those guys in liters if you like. Taking that, we got 0.1 times 1,000 divided by 1,002. Going to get us something like, what we got there? That's calcium, sorry. Wrote the wrong ion there. That don't look right. Take 2, that's actually calcium I'm doing here. There we go. So calcium is 9.98 times 10 to the minus 2 molar. We want to do the same thing for our hydroxide here. Hydroxide, again, we're taking 0.2 molar and we're adding 2 milliliters of it. Again, total volume is 1,002. And just like with our calcium chloride, this is really the only source of hydroxide that we got going on in this case. So in this case, we would have 0.2 molar, 2 milliliters divided by 1,002 milliliters. And that gets us, looks like 3.99 to the minus 4. Any questions up to there? At this point, what's left is pretty much, we just need to put it into our expression here. So putting those numbers in gives us a Q value that is 9.98 times 10 to the minus 2 times 3.99 times 10 to the minus 4. Again, don't forget, we need to square it. And if we do that, do a little squaring action there, and a 9.98 to the minus 2. Going to get us a Q value of 1.6 times 10. That's a lot of zeros, so I'm going to go with minus 8. Any questions on that point? Our calculation there. All right, so now that we've calculated that, what does it mean? Well, we now want to take our Q value and compare it to the KSP value. Our Q value is 1.6 times 10 to the minus 8. We really can just compare the top number there. That's to the minus 8. Our KSP value from the table is to the minus 6. And what we see in this case is minus 8 is smaller than minus 6. That means Q is less than the KSP. That means we would expect the equilibrium to shift to the right. And remember, in these reactions, we have solid on the left of the arrow, aqueous ions on the right, and that means that we would expect no precipitate here. Any questions on that? So here we see the third sort of effect on solubility, which is, again, even though based on solubility rules, we would expect a precipitate to occur between calcium and hydroxide. We're actually not going to see it here because, well, our concentrations are not good enough in that sense to allow a precipitate to actually form. Any questions on that? So those are 3 really big factors in terms of effect on solubility of, say, a compound. If there's a common ion present, it's going to really decrease the solubility. The pH of the solution, especially if there's hydroxide or H plus involved with an acidic salt or basic salt, can either increase or decrease the solubility. And the third really important thing is concentration. So although you may have the right ions in the solution to make a solid, the concentration of those ions may not be sufficient enough to allow that precipitate to actually occur. So that's a very big thing in terms of not really seeing the solid form. Any questions on that? And that's actually in those type of experiments I was talking about just a second ago, which are those qualitative analysis experiments. This is really a big factor in terms of whether or not you sometimes see a precipitate happen. Because if you think about it, and if you ever maybe have done an experiment like that, or just an experiment in general, when you add reagents, right? We oftentimes don't think about this aspect of it though. When we add reagents, although we're adding the reagent that we are looking to add, say we want to add some sodium chloride or we want to add some sodium hydroxide or whatever it may be, we oftentimes think about the reagent as we're just adding that reagent. But a lot, obviously, of solutions that we add, a lot of them are aqueous, right? And what does aqueous really mean? Aqueous really means that it is a water environment. And what that means is, and sometimes not really picked up by students is, or people in general, when they're doing experiments and they continuously add sort of solution. And maybe you're not very careful about how much you're adding. Maybe say a couple of drops, you just keep adding and adding and adding. What you're doing every time you add a reagent is you're essentially doing a dilution. So you're lowering the concentration. And in a case where you're trying to maybe precipitate out some ion, you may actually have made it too dilute for the precipitate to actually occur just by not adding water, like go from the shelf, picking up water and dumping it in there. But again, by adding those reagents, every time you do so, you're essentially doing a dilution. So if you're not very careful when you do that and you just keep adding and adding, or go, okay, I'll add this, I'll add this, I'll add that, at some point you may actually over dilute your actual solution. All right. Speaking of sort of that idea of qualitative analysis type experiments, a very sort of common theme of that type of experiments, and really a very useful sort of theme of KSP is the idea of what is sometimes referred to as selective precipitation. So what does that mean? It means, well, maybe you have a beaker, for example, or a test tube like we have in the picture, or just in general. And in this test tube or beaker or whatever we may have, floating around the solution, we'll use the example here in this problem, you have some bromide ions that are floating around. You also have some chloride ions that are floating around. So they're happy, they're floating and all this good stuff. And you decide, well, I want to precipitate them out. I'm going to add silver to it, which seems like a good idea. So you add some silver, maybe some silver nitrate as a source of silver. And congratulations, you get a precipitate. You can get silver bromide to precipitate, or you could get silver chloride to precipitate. What is the problem with maybe just dumping in the silver without really thinking about what the situation is? Well, the problem is, as we see here in these test tubes are silver chloride and silver bromide, right? So these are a test tube of basically silver chloride and silver bromide. And if you look at both of these, that's like a white solid, that's like a white solid. So if we added silver just to this test tube that had both of those ions floating around in there, we would induce, again, a precipitation of both silver chloride and silver bromide perhaps happening together, which means if you wanted to really, for example, only take out one of the ions, like say the bromide ion first, and you just added the wrong amount of silver, you would actually see both of them come out together. And you can't kind of look in there and go, well, this little white precipitate, I think is silver chloride. This one, it kind of looks like silver bromide. This one looks like silver chloride. There would be really no way to distinguish sort of what ion you brought down with the silver, because in this case, they actually make the same color precipitate. So we could use basically KSP and use it to our advantage to really figure out how to, for example, selectively precipitate out only one of the ions that are floating around, but keep the other ions basically still floating around in the solution. So for example, in this problem here, specifically, we want to precipitate out only silver bromide, which means in this example, what we want to do is just take out this guy with the silver, basically as a solid. We want to leave the chloride basically still floating around in the solution. What we know about these ions is both of these ions each have a concentration of 0.02 molar in this example. So we could use our KSP basically to help us do that. Here's our KSP reaction for silver bromide. Here's our KSP reaction for silver chloride. And again, our KSP values that we could find from the table. Now, looking at our silver bromide, if we write the KSP expression for it, again, it's going to be our product. So that's going to be silver times bromide. And that again is going to equal 7.7 times 10 to the minus 13. Well, I want to know really how much silver I need to add. The good news is I already know the concentration of bromide. It is 0.02. Rearranging the KSP expression and solving for silver, which basically means we're just going to divide the bromide to the other side, gets us 7.7 times 10 to the minus 13 divided by 0.02, and that will get us we'll call it 3.9 times 10 to the minus 11 molar. So what does that number actually represent here for our silver bromide? Well, that number is the minimum concentration of silver needed to start precipitating silver bromide. So you could add silver and you will not see a precipitate form of silver bromide until you hit that concentration of 3.9 times 10 to minus 11 in terms of the silver guy. Any questions on that there? Well, that's good for silver bromide, but what is the deal with silver chloride? What is the silver concentration needed for silver chloride? We basically could do the exact same calculation. The KSP is equal to our silver in this case, times our chloride. Again, 1.6 times 10 to the minus 10. We also know the concentration of chloride floating around that solution. It is also 0.02. That means just like above, we can rearrange and solve for silver. Giving us 1.6 times 10 to the minus 10 divided by our 0.02 molar, which is our chloride concentration here. And we hit a number of we'll call it 8 times 10 to the minus 9. That's a lot of zeros. So what does this number mean? Well, this number means exactly what the number above means. This number is the minimum concentration of silver needed in this case to precipitate out silver chloride. Any questions on that? So if we wanted to answer this question based on what the problem's asking is, we only want silver bromide to come out. So we basically only want to get rid of this guy and we want to keep the chloride still floating around. That means that the first thing that we need is we need to get our silver concentration to 3.9 times 10 to the minus 11. At that point, we should start to see silver bromide precipitating out. We need to keep the concentration of silver greater than that number to precipitate out the silver bromide, but we need to keep it less than 8.0 times 10 to the minus 9 molar, because that's where we start to see silver chloride basically start to precipitate out. So if we add in this example here silver again from something like perhaps silver nitrate or something like that, at a concentration of 3.9 times 10 to the minus 11, you should start to see some white solid form. If you want to increase the amount of silver, you can. You can continue to increase it as long as you keep the concentration less than 8 times 10 to the minus 9. And you should still continuously see white solid going out and precipitating out and precipitating out. At some point, if you keep adding the silver nitrate and the silver, so again, as long as you keep the concentration below 8 times 10 to the minus 9, you'll see white solid, and at some point you may stop seeing white solid. At that point, if you stop seeing white solid, you could probably safely assume that you have now removed all of the Br minus from that solution. And if you did that, the only ion that you technically would have left, I'll draw it dramatically here, this would be all, it's obviously now turned to a red solid, which it is not, but we'll assume here. This would be all the silver bromide. That's a lot of it, by the way. But now you can assume that pretty much if you saw no more white solid form upon addition of silver nitrate and is still below 8 times 10 to the minus 9, you could assume that the only ions floating around in that solution now are the chloride ions. What you might want to do is centrifuge this out, pour off the liquid, do some type of centrifuging. When we centrifuge, we spin it around really quick. Solid goes to the bottom, liquid goes to the top, pour off the liquid. And now you would have pretty safely assumption that you would have just a solution that contains chloride. So what would you have to do at this point? You then would have to increase the silver concentration to 8 times 10 to the minus 9 or higher. And once again, once you hit that 8 times 10 to the minus 9, you should start to see some solid form again. And at this point, you can feel pretty safe that this solid is silver chloride. So by controlling, in this example, the silver concentration and using our KSP sort of values to help us understand what concentration is needed, we can, in a process, precipitate out the bromide as silver bromide first, leaving the chloride still floating around. Once we feel very confident that we have got rid of all the bromide, we don't see any more white solid forming, we increase our silver concentration, in this example, to 8 times 10 to the minus 9. We once again should start seeing some white solid form. That again is silver chloride in this case. And now we're selectively taking out the chloride. And again, you would do that until you don't see any more solid come out, and you can feel confident you got all the chloride out of the solution. Any questions on that aspect of it? Now, one last thing here before we move on from this example that also ties into something we talked about at the very beginning of this chapter here is the idea of KSP values. And can we use KSP values to help us decide which salt would be, or which solid would be more soluble or less soluble? And if you remember, there is one situation where you can use the KSP values to sort of predict which solid would come out of solution first, be less soluble, and which one would be more soluble. And it's a situation where each of these compounds break apart into the same number of ions. And if we look at silver bromide and we look on the product side there, it breaks apart into 2 ions. If we look at our silver chloride, it breaks apart into 2 ions basically, right? So in this situation, because they both break apart into 2 ions, we can directly look at the KSP values for both of them. And what we see here is the KSP value for silver chloride is larger than the KSP value for silver bromide. So what does that mean? If you remember, the one with the larger K value, a large K value means that we mainly have products. And since we have products, that means that we would expect silver chloride to be more soluble than silver bromide. And that is why in this particular question, it asks you to precipitate out first which one? It asks you to precipitate out silver bromide, because based on the KSP value, we can make a pretty good assumption that between those two, the silver bromide is going to be least soluble because it has the smaller KSP value. And again, we can make that comparison because they both break apart in the same number of ions. Any questions on KSP, factors that affect solubility? So earlier I was talking about this experiment, which is known as qualitative analysis. And again, should be happy, I suppose, that they don't do these experiments anymore. Years ago in this class, like the second semester general chemistry, you did pretty much these experiments the entire semester. So the good news is there's a lot of really bad sort of chemicals and smelly chemicals involved in these experiments. So good news is you don't really do these anymore. Some schools still do, but a lot of schools don't do it anymore. But really what qualitative analysis is there's different groups. And when we talk about groups in qualitative analysis, there's group 1, group 2, group 3, group 4, and group 5. And sometimes these guys are kind of combo together. And when we talk about groups here, though, we're not really talking about groups on the periodic table. We're talking about groups based on solubility, basically. So these are really groups based off of solubility kind of rules and precipitates. So for example, if we look at group 1, that's silver, mercury 1, and lead 2. If you remember your solubility rules, things like chloride, things like bromide, things like iodide, they're pretty much soluble in everything, but there are 3 exceptions, and those 3 exceptions is these 3 guys right here. And so these 3 exceptions allows us to separate out these guys as precipitates. So in these sort of qualitative analysis experiments, the whole goal of sort of qualitative analysis is we want to really, we have a beaker or a test tube that basically has ions from group 1, maybe group 2, group 3, group 4, group 5 in there, and they're all floating around. And we want to individually identify what ions are present. In order to do that, we actually do a lot of selective precipitation. So we would add in this case what is referred to as a group reagent. So hydrochloric acid is a group reagent for group 1. And that's because when we add hydrochloric acid, that's an H plus and Cl minus. It's basically a source of Cl minus. And when Cl minus hooks up with those 3 guys, that is going to make a precipitate, basically chloride precipitates for those 3 guys. It's going to basically grab those 3 guys out of the solution. At that point, you would have precipitated out group 1 from, say, group 2, group 3, group 4, and group 5. You then would take that precipitate that has like silver chloride, mercury 1 chloride, and lead 2 chloride, and you do some more sort of experiments on it and basically individually take out each of the ions and do a specific test that says, oh, I found silver, or I found lead, I made a yellow solid down the road, or something like that. You then would do the same thing for group 2. And again, these guys are group 2. Again, they're related to each other based on solubility. We use basically hydrogen sulfide gas, which is a very toxic, deadly type of gas. And it basically produces sulfides. So a lot of sulfides are insoluble. It makes a lot of these sort of sulfide guys. And here's what the difference is, for example, something else we've been talking about. If you go to group 3, you will also see that the hydrogen sulfide gas is also the group precipitating reagent, also providing sulfide. The difference, though, between those two groups is something we just talked about that affects solubility, and that is pH. In group 2, we use that hydrogen sulfide gas under very, very acidic conditions, like you get it down to a pH of 0.5, so very, very acidic. When we get to group 3, what that will do, by the way, if we did have group 2 and 3 in a test tube floating around together, because we made it so acidic, it will only allow group 2 ions basically to precipitate out. These group 3 ions would stay in the solution. Now, once we've got rid of group 2, we're just going to basically turn the pH really basic in this case. And that, by doing that, is going to increase the hydroxide concentration. And as you can see here, we get both sulfides and hydroxides to precipitate out. So this is, again, kind of what we were talking about a little bit earlier here today. By playing with the pH, even though we're kind of using the same thing to precipitate out these ions, because one is so acidic, it will allow certain ions to stay in solution, even though you're adding something that technically should make it precipitate. But because the pH conditions are not right for those guys to precipitate out, they'll stay in the solution and keep floating around. Then when you make it basic in group 3, now the conditions are right. They're going to basically come out of solution and precipitate out. So again, these are the things that we've been talking about, things like concentration, things like pH, that have a very big effect as to whether or not you see a precipitate actually form, even though solubility rules tells us it should. And it also allows us to really play with sort of concentrations, play with conditions to do what we just talked about in the last example, selectively precipitate out certain ions while keeping other ones basically in the solution. Any questions on that there? By the way, at the very end there, group 5 and group 4 and 5, those are things that are typically soluble in everything, things like sodium, potassium, ammonium. So we oftentimes will save those guys to the end. Here's what people typically look like as they're doing this experiment. But we also sometimes will use flame tests because of that. So obviously when we get to things, for example, like sodium and potassium, these guys are pretty much soluble in everything, although there is oddly a weird test you could do to actually precipitate out potassium. But most of the time, potassium, sodium is pretty much a soluble guy in everything. And that means that sometimes we do have to rely upon flame tests. And you probably have done flame tests before or seen flame tests before. When we do a flame test, we're essentially exciting the electrons. Electrons go to a higher energy level, right? And then decide they want to come back down. When they come back down, they give off energy in the form of a wave. That wave corresponds to like the visible part of the spectrum. All this is happening very fast, obviously. And we see a color, right? So like sodium is yellow. Again, if you cooked pasta or something on the stove or boiled water, maybe it's overboiled at some point and the water hits the flame and you see that kind of yellowish color come out, usually because there's salt in the water. And that's actually the sodium ions that are getting excited by the flame. Potassium is purple. And even things that actually do make precipitates, for example, copper and things like that, we could even use flame tests to help us sort of identify those things as well. Again, these sort of ions do give off, our metals do give off oftentimes distinct colors that we can look at. Any questions on KSP? So the next thing we're going to talk about is another equilibrium type situation. And this actually has to do with what is referred to as complex ions. And complex ions contain a central metal cation that's bonded to one or more molecules or ions. A ligand is usually a Lewis base. So what we have here is basically what a complex ion is. It's a metal. Gotta put it there. It's a metal. And attached to that metal is a bunch of ligands. And what are ligands? Ligands are Lewis bases. So if you remember, we talked about Lewis acids and Lewis bases. And a Lewis base is a substance that will be an electron pair donor. So it will donate a pair of electrons. It will basically donate a pair of electrons to our metals. So if you think about metals in a complex ion, these are usually a lot of times transition metals. Can be something like aluminum as well. And I think we came across some of these guys when we were talking about salts and hydrolysis. But they usually have a fairly good positive charge. And what that means is they're essentially electron deficient, right? So if you think about that sort of definition of Lewis acids and Lewis bases, the metal being electron deficient means it acts as a very good Lewis acid, right? It's going to want to accept that pair of electrons. The ligands is going to be the guy that will basically accept the electrons. I'm sorry, the ligand will be the guy that will donate that pair of electrons in. So if we look at something like this, this is our metal. This is our ligand. And again, chloride is a very good ligand because it needs to donate a pair of electrons and it has a negative charge, which implies that it has gained some electrons, it's willing to give up some electrons and so forth. And we get this complex ion, which in a later chapter, we will learn how to properly name it rather than that thing right there. It will learn to name it as tetrachloral cobaltate 2 ion is basically the name of it. And again, in that later chapter, we'll talk about naming that. So it does set up an equilibrium, and this equilibrium is what is known as Kf. And this is the formation constant. And this is basically the equilibrium constant for this complex ion. Even though it's Kf, it is done exactly like everybody else, except it kind of looks a little messed up there. So maybe I'll rewrite it there so we can kind of see it here. Let me just make sure here. Where'd it go? We'll just cross it out real quick. Top part looks a little funky. It is the concentration of CO, Cl4 2 minus, again divided by CO2 plus. And again, our Cl minus. We don't want to forget the 4 there because we have 4 of these chlorides basically going on. So in this particular case, what we have is a cobalt, and attached to that cobalt is 4 chlorides, basically here. So why is the overall charge -2? Well, each of these chlorides is -1. Cobalt is +2. So +2 and -4 gives us a -2 overall, which is, again, why the charge here is -2. So when we look at a Kf value and the Kf value increases, the stability of the complex ion also increases. So what does that mean? Well, when we have a larger value of K, that means that we would expect more products in this case. And in the case of this Kf equilibrium, more products would mean we're heading in this direction, and this direction is our complex ion. So that's what it means. The larger the Kf value, the more stable the complex ion is, and we would expect the complex ion to be formed. Now, depending on sort of the ligands attached, in this case, water is a ligand. Water is a good ligand because water also is a polar molecule and has those non-bonding electrons there on the oxygen, which makes it a pretty good ligand. Here's our Cl over here. These both were really cobalt with a +2 charge. And a couple of things are different here. We have different ligands attached. We also have different actually geometry of these sort of complex ions. One is an octahedral sort of arrangement with this guy. And this guy over here is more of like a square planar or tetrahedral arrangement. And because of that, we actually see some different properties. So the cobalt's kind of pinkish with it in water. Cobalt's more blue in color when it's in with the chloride. So again, it does have some of these effects. So what makes something sort of a good ligand? As I mentioned before, It's a Lewis base. So basically what that means is it does usually need to be something that is negatively charged, or it needs to be something that is polar and has some non-bonding electrons, like the case of water, like the case of NH3. Again, if you drew NH3, looks something like this. Again, polar molecule with those non-bonding electrons on the nitrogen, going to basically make it a very good Lewis base. Another important thing that we talk about when we talk about complex ions is what is sometimes referred to as coordination number, CN. The coordination number is how many atoms are directly bound to the metal. And it gets a little tricky in some situations, and we'll talk about it again in sort of a later chapter when we get to that chapter. But if we look at something like our cobalt in water, what that means is, again, we have our cobalt sort of in the middle here. And when water attaches, it's going to attach through the oxygen, right? That's where our non-bonding electrons are. And if we do this and draw in our 6 waters here, got left just enough room, got one there. This is basically our complex ion. Again, this whole entire thing here having a +2 charge. Now, when we look at the metal and we look at how many atoms are directly bound to it, there's 1 there, there's 2 there, there's 3 there, there's 4 there, there's 5 there, there's 6 there. This guy would have a coordination number of 6. Same thing with our cobalt and our chloride, like I drew sort of back on this page. Attached directly to the cobalt here is 1 chloride, 2 chlorides, 3 chlorides, and 4 chlorides attached directly to it. And the coordination number for that guy would be 4 here, as we see. Now, you may be saying to yourself, well, isn't it just this number on the bottom? That's 6, and that is 4. And the answer is not always. In these two cases, or in the cases actually of anybody that's listed up here, these ligands are what are referred to as being monodentate. Monodentate, mono meaning 1, which means for every water molecule, for example, there's only 1 atom in it that will bind to the metal. So in this case, the oxygen. In the case of the Cl, there's actually only 1 atom to begin with in Cl, so it can only bind in 1 place. Same thing with NH3. It is just the nitrogen that makes that attachment. There's also some ligands that are what are referred to as being bidentate. Bind in 2 places per molecule. There's some that are polydentate, which means it could bind in more than 2 places per molecule. So for